Good evening, everybody. If everybody can, if you're still out there grabbing a bite to eat, if we can have everybody come on in, we're about to start a very, very interesting presentation this evening. First of all, I would really like to thank you for being here this evening. For those of you that don't know me, my name is Milton. I am the Zoological Education Director for the SeaWorld Research and Rescue Center, as well as the park. For those of you that know Dr. Elise, she is on very important scientific business right now. So I will be facilitating tonight, but I would really love to introduce you all to Dr. Claudia Stauber, Claudia Stauber from the Emirates Natural History Group of Abu Dhabi. And what an interesting subject. Still, every time I come and I look at all the faces here, what fascinates me is the diversity of this group, the age groups that are coming here. It's so magnificent to see people of every walk of life coming to enjoy these very important talks in science and what we do here at the center. Understood when we filled up for sharks and some of the other subjects, but to have a group here that's interested in tectonics is just fantastic. So I'm just going to ask for those of you that are here. Let our speakers finish through that. And for those of you that have your children with you, please join in, enjoy the presentations, and we'll have an interactive session at the end. And Claudia, over to you.
So thank you for the introduction. So I'm the chair of the Natural History Group, and I'm a geologist myself. So I was absolutely thrilled when the audience requested today's topic, tectonics. And even when we are here in Abu Dhabi in a tectonically stable area, the larger Arabian Plate has magnificent examples from many different tectonic processes and offers unique insights to the ongoing and past dynamics of our planet. We are happy to welcome two experts of the region that will let us experience tectonic from different perspectives. Dr. Pavlopoulos and Dr. Abdel Maksud, both are sitting here. So I will introduce quickly both speakers. Dr. Cosmos Pavlopoulos is professor at Sorbonne University, Abu Dhabi. He is coming from one of the tectonically most active regions of the world, Greece, where we have just in one small area around 19,000 earthquakes in the past week. So we all don't know why exactly. Dr. Cosmos holds a PhD in the environmental geomorphology from the University of Athens. He specialized on quaternary and marine geology, sea level changes and geomorphology in the region and beyond. And Dr. Cosmos will give us an introduction to the Earth dynamics and Arabian plate evolution. Our second speaker, Dr. Ahmed Abdel Maksud, is from the Earth Science Department of Khalifa University. Dr. Abdel Maksud is a structural geologist specializing in tectonics and marine geoscience. He earned his PhD from Khalifa University in 2024. He will present parts of his recent scientific work as postdoctoral scientist at Khalifa University, where he could make new and significant contributions to the geology of the region. His research was just published in the journal Nature at the end of last month. So congratulations to him. The scientists here already congratulate him. They know how important a Nature article is for the future. So, and Dr. Ahmed will speak about UAE tectonics and discovery of pockmarks in seafloor gas venting offshore Fujairah. And we will have the question and answer setting at the end of both talks. And I will give now to Cosmos, Dr. Cosmos,
Thank you very much, Claudia, for your kindness and the presentation. I only ask change. Yes, this is important, but it's okay. I'm really coming from a small country, but the last 2 weeks we have more than 2,000 earthquakes, especially in Santorini Island. It was a mixed situation. Thank you. I think,
It's on.
oh, perfect. More than 20,000 earthquakes in between fault zone and magmatic chamber. But this is another presentation, let's say. I remove it from my presentation. What is tectonic? It's tectonics, and that is the most important essentially somewhere. The layout of my presentation will be the introduction for my colleagues after. What is tectonics? Earth structure and layers, lithosphere, material stress response, tectonic plate motion and boundaries, driving forces of tectonic plate motion and plate tectonic, and the significance, and Earth system habitability. Tectonics comings, unfortunately, for the Greek ancient word tectonikos, that's mean pertaining to the earth. The geologists will use that as the architecture. And in the presentation, we can read more. I would like to be more comprehensive for the new generation and for the non-specialists. And it's a long-term process, generally, and fundamental for the and affect the earth structure and the surface as well. That you can see is one of the last works by Van Dijk, not the footballer, but one colleague of us, and that present, I'm sorry, back, yes, the tectonic imprint, if let's say, based on GIS, that's mean Geographical Information System, about the different kind of tectonic expression of the Earth's surface and the bottom of the sea, the floor of the sea. Coming from the boundaries of continents, fault zones, and so on. 11,000 elements was introduced in this dataset based on the literature review and the classification of the most recent of their science. Focus on our area are not the faults in general, but the major fault zones, and I think be more specific after that the presentation. But all are dependent about the structure of the Earth, and this is totally important. You can imagine the structures of the Earth like an orange, that we have the inner core that is totally solid, the outer core that is liquid and to play an important role about the plate movements, and above them 2,900 approximately kilometers of mantle with solid, molded in some cases, and arriving at the upper part of the mantle and the crust, but the crust is totally solid, and I don't like to say floating, but as a conveyor belt, moving on the top of the mantle, upper mantle, asthenosphere, as we talk about, and the part of the asthenosphere and the crust consisting the lithosphere, and the lithosphere plates, as we will see. One big question is how we know about that, if we really think that the crust is around 5 to 60 kilometers, and the deepest borehole on Earth is not more than 12 kilometers. For that, my colleague geophysicists know much better than me how we can go deeper and scan, like not the echo sounders, like the doctors do for us when we do some ultrasound and so on, to scan the interior of the Earth. And based on the seismic waves that can, some of them P are the primary, S are the secondary, can get through liquid or solid material, as waves have some shadow and cannot be transferred into the liquid material. And as we know till now, we have separated, and the Earth is separated in 16 major plates. And of course, I would like to add more of subplates that we call sometimes terranes. And hope that's worked. That is an interpretation about the plate tectonic movements through time. The number that you see running out are mega eons, that's mean millions of years, and you can see how part of the continents was before on the southern pole, Antarctica today, as was Arabia approximately 500 million years ago, and starting to moving up, that's mean near the equator, all these hundreds of millions of years arriving almost in our place. You can see India moving up fast, collide with the Eurasian plate and create also that we talk about Himalaya mountain. That means you see that the internal processes really are drivers, and we would like to see who is in brief the mechanism of that, to create big mountains, volcanoes, as we will see, and of course, not only on the land surface, but of course on the floor of the oceans. And that is totally important, as the water column and the sediments, as we said, of the bottom of the sea are connected and interconnected with the atmosphere. We have three different plates boundaries. That means the divergent, as are totally important as we are in SeaWorld today, that to create or is the basement of the ocean of the world. When one plate is moving apart from the other, and the magma coming from the asthenosphere go out of the bottom of the sea, created the ocean rifts. Second is the convergent, which one plate subducted, that means go below the other for different reasons. And of course, we have the transformation movement on that. Here you can see a global image about that. You see the Arabian plate almost on the middle of the map. More dedicated maps, but from these slides, note that as you see in blue are the mainly oceanic crust. That's mean that are part of the extended ocean basin based on the movement of the Mid-Atlantic ridge or East Pacific ridge or Indian Australian ridge. They move the continents and the part of the plates as well. And specific numbers that you can see there correspond to for centimeters per year are really measurement with accuracy based on GPS or GNSS, as we said about. But what are the driving forces? As you understand, step by step, Earth is alive and kicking. Who gives the force to do that? A couple of years ago was only the mud convection currents, but that's are warm mud currents that as conveyor belt can move the plates along each other. Ridge pushes and slab pull. Here with this figure, I think is more comprehensive. The convection traction move the plates of the lithosphere apart each other or subduct each other as the slab pull. The ridge push means that extension of the plates refers to gravity of the lithosphere, remove or move the mid-ocean ridges into the atmosphere. And the slab pull, when the cooled part of the lithosphere is engine down to the asthenosphere and, of course, dragging the rest of the plate down into the mud. Here is a model animation, so the mud convection currents, how it drives the plate tectonics. That's when you see that the interior of the Earth is really very active. But the key point is what we see at the land surface as we live on the land surface, and 70% of the population lives on the coastline, as the major cities of the Earth are located there. The key point is the response of the land is dependent on the material, and the material are the rocks, and the rocks are not homogeneous, that means are not the same in every location of the Earth. And various type of forces considered of its rheology is the name, is that's mean how knowing how its flow. Describe the interaction between strain, stress, and time. This diagram is totally easy, I hope so. Forget about plastic or elastic deformation and straight to the brittle, because the brittle deformation provide to us that we don't like to live with them are the earthquakes, the volcanic eruption, and the plastic or ductile, which are irreversible as well, deformation, provide to us nice landscape and mountains buildings sometimes. Of course, there are some threshold, yield point about plastic deformation, but that provide the earthquakes at the end of the day are the fracturing. That means the brittle deformation. I don't like to stay long time about the type of faults. We have, based on the extension, the normal fault, generally, compression reverse fault, low angle, the thrust fault, and right lateral or left lateral strike slip fault as well. What give to us? We have some really morphological differences in between them. This is the mirror of the fault, the slicken side, as we talk about. Similar also in coastal areas, and you can imagine that all these landforms on the land, we can really meet them at the floor of the sea. And we have, let's make an example, more of the active faults in Greece are submarine fault zones. Active faults continue to cut the rock till the surface, and the inactive is stopped in one level of these layers of the rock. Combe, 1995. Most of you, not maybe we didn't be already born, but in 1995 in Kobe, we have earthquake, another cause seismic event as is the liquefaction, when we have the sound and we have earthquakes and the groundwater level starting to moving up. The sound behavior is like a liquid and destroy all the construction that we have or more of them. This is the folding that can provide mountains, if you like to say, that's mean ductile deformation that could be and provide to us very nice faults with different classification as well, but totally that are some of them in metamorphic rocks, provide the most impressive landforms at the Earth's surface and also at the bottom of the sea, as Mariana Trench in the subduction zone between Mariana terrains, that means subplate in between Philippines plate and Pacific plate, and the higher mountain in our planet, Himalaya mountain, after the collision of India with the Eurasian plate. Ants mountains, really impressive, starting from the right hand from Patagonia mountains, some of the southern European Greek mountains. Of course, we have different landforms, as you understand, because they are not exist on the Earth, only the internal processes. That means that's start for the interior Earth dynamic. But you can see there are more ends, that's main glacial deposit of the past, in one of the southern part of Europe, in Crete Island, that's been in the front of Egypt and Libya. Provide a framework for understanding earthquakes. That means the geologists and the geophysicists were very happy when an earthquake is happening, because we have the energy and the power and the seismic waves to study the interior of the Earth. Honga Tonga Hapai underwater volcano, 2022, one of the biggest volcanic eruption of the world, that volcanic material, not only dust and volcanic ash, was spewing up to 58 kilometers to the atmosphere, and it should generate a tsunami of 15-meter height. destroying the village, creating a sonic boom that rippled around the world twice. And also, a few days ago, we have by INGV, Istituto Nazionale Geologica Vulcanica of Italy, the monitoring of volcanic eruption of Etna. This is Sicily, active volcano in Europe, southern Europe, and of course, eruption a few days ago. And as Claudia already mentioned about Santorini Island, which is an active caldera providing a lot of earthquakes. We worked there last year. We published about the risk zones, and it's a really tricky situation in between active tectonic zone and magmatic chamber and magmatic activity. Nobody knows if it will be exposed or if we will have a big earthquake. A small introduction for you about Arabian Peninsula and tectonics. We have everything in Arabian Peninsula, if you like to say, everything about boundaries, tectonic plate boundaries, starting on the northern part by the transformation fault of Anatolian plate and Arabian plate, the Dead Sea transformation fault, horizontal movements. We have the divergent plate in one of the newest oceans of the world, Red Sea. You can read 16 millimeters per year. We have also subsidence, or we have convergent plate in the Chagros Thrust, Macron Thrust, and of course we have other micro fault zones, on fraction zones, horizontal movement, transformation faults, and we have also that we talk about the Afar triple junction point. That is rare, a little bit to see in a small plate as Arabian plate. In between the Dead Sea transformation fault, as you can see, the African rift and the Afar triple junction in between Gulf of Aden and both of them. Before I give to you the field, there is the big question. Are United Arab Emirates have earthquakes or not? As Claudia said at the beginning, yes. Normally, we do not have earthquakes or big earthquakes at the area of United Arab Emirates. Of course, we are nearby a big seismic zone of Zagros Mountain on the northern part of Iran that provide frequent and high magnitude earthquakes. But the last earthquake happened in UAE was in Masafi, 2002, approximately 5 magnitude of Richter scale, was the epicenter. You can see in between Horfakan and Diba fault zone, and that is 2006 publication by Roger et al. And you can see how many earthquakes are recorded to the Iran area, Zagros Mountain corresponding to the subduction zone, and not bad number of earthquakes, more than 3 Richter magnitude scale to the northern part of the Emirates. Here also, you can see the continental crust, how it's transformed by Zentan fault zone, and how that affects the seismicity of the northern part of the Emirates. We have, and we had some earthquakes event. The Masafi, as I said to you before, but we have also in 1945. 1945, not here in UAE, but in the Makran subduction zone, 8 Richter magnitude produced a big tsunami that affect especially the Omani coastline, the Indian coastline, more than the Fujairah and the Horfakan area, coastline area. And of course, we have another one in 1978. And if we see some modeling about the propagation of the tsunami after the Makran seismic zone event in 1945. You see the tsunami that is generated in Makran zone and propagated to the southeast direction, affecting Mumbai and the Indian coastline more than the Omani and, of course, Emirati in this period area. We have hopefully the seismic hazard zone map revised as well, that as you can see in brief, the northern and eastern part of the Emirates are more in higher seismic zone, not only by the Masafi fault or Tiba fault zone, but affected more by the earthquake of northern part of the southern part of Iran and Makran zone. The area of the western part between Abu Dhabi and western region is really low to very low, and there are very accurate and reliable risk assessment studies that really can provide of all of us. Concluding, the significance of the place tectonics are not only the earthquakes, the volcanoes, the mountain buildings, or the recycling of the crust and the cycle of rock, are related with the distribution of natural resources. In large scale, are related with the evolution of life, and believe me or not, are related with the climatic variability. And that's play really a very strong role on that regarding the past geological period, as we have the PETM, Paleocene, Eocene thermal maximum, that really affect the marine life. We have extinction of a lot of species. Of course, the CO2 emission by humans didn't exist. And there are some hypotheses about that, and especially for one of the biggest driving forces, as there are the volcano and the volcanic eruption, that can really provide huge amount, not only of CO2 and vapor to the atmosphere, of course, dust and volcanic ash and other gases that can really affect or drive the acidification to the ocean in more dangerous level. This last approach is how the long-term contribution to the plate movements contribute to the tectonic carbon conveyor belts. That's mean massive amount of carbon between the deep earth and the surface exchange. The subduction zone, and of course on the spreadings of the oceans. Last approach is that connecting Earth spheres, that's meaning between lithosphere, biosphere, and atmosphere, are interconnected. All colleagues of mine can really refer to Lovelock theory about care that could be and must be, and there are a lot of relation between the atmosphere and the internal processes and the plate movements. Tectonic plates giving Earth in long-term scale, varied landscape, not only building mountains, volcanic islands, and so on, but deep ocean trenches, affect the climate in long term, and of course the change of the ocean current and wind could be and contribute at the evolution of life as a raft for a long time period for most of the species. Finally, I would like to say to you that, of course, we have short-term impacts to our lives about the plate movements regarding earthquakes, regarding tsunami, regarding uplift or subsidence of the coastline that can really affect our life and area, and of course can really change the sea level, and because of that we talk about relative sea level. I think I'm finished. Thank you very much. I'm open for questions.
Much for your talk.
I hope that I respect the time.
Yeah, perfect. We will have all the questions questions at the end of both talks.
Thank you very much.
I think this is best. And now I give the micro to Dr. Ahmed. We are looking forward to your talk.
Hello everyone. Assalamu alaikum. Actually, it was fascinating to know that people want to listen or know about the UE Tectonics. And today I take this a chance to speak about the UE Tectonics and also about our recent discovery of some seafloor gas seeps offshore Fujairah. So I'll explain a few terms that I mention frequently in my presentation. The first thing is a normal fault. Normal fault means that some part of the earth moves down relative to the other part. The second thing is thrust fault, which moves up relative to the other the surrounding area. And also folding, which is came from or affected by compressional faults. The one bended upward is called anticline, and the one bended down is called syncline. I'll also mention the term salt dome or salt diapir, which forms when we have some salt in the deep subsurface, and when there is differential changes in the pressure, the salt could migrate upward and push and dissect the overlying layer to make this shape, which is called the salt dome. The last term is the basement. Basement means the end of the limit between the sedimentary sequence, the sedimentary layers, and the metamorphosed and igneous rocks that are buried very deep within the Earth's crust. I'll start with the geological evolution. I'll speak exactly about the UAE. Here we can see this is the UAE here. So let's focus on this part and let's travel back in time. Sorry, I'm trying to control it. Okay. It's not starting. Okay. Yes. Now we go back into the Permian time is around 260 million years ago, and we see this is the start of a new ocean. We see that this ocean has just been opened. This is the new Theseus Ocean. Going again with time into this timing around 150, we can see more spreading of the ocean. And later on in the Cretaceous time, we see the ocean started to close down. Now it started to close down here. And we see that this part started to go above this part till at the late Cretaceous time is around 90 to 80 million years ago. This part of the ocean, all the oceans, the new Theseus, totally override the Arabian Plate. So now this part went above the Arabian Plate, which this situation is called the ophiolite abduction. So now here we have the abduction. Now we have a load that has been sent over the Arabian Plate. That load caused the Arabian Plate to flex down. So now we have a load. The crust will flex down. This flexure will create an area and space area for deposition. And this area, the far area, would be bulged upward. So now we have the load. We have the basin here, it's called foreland basin. This basin foreland. And here we have the bulge area. So this situation was in the late Cretaceous, maybe around, you can see around 80 million years ago. So what happened next after that? This is a present day situation. This is a present day situation as a cross section. This cross section we can just imagine, and this is across the UE, from the western part and across the mountains. Here I want to show you where exactly we have this section. Here we have Abu Dhabi, here Dubai and the Northern Emirates, and this is the border of the UE. So let's talk in detail about the different tectonic provinces of the UE. The first part is the hinterland basin. Hinterland basin is the extreme eastern part of the UE, and this part is full of normal faults. That's full of normal faults. The next part is fold and thrust belt. This belt, as you can see, is full of thrusts, the rocks that has been thrusted and also compressed to make folds and thrust. The next one is the foreland basin, as I mentioned, that has been formed as a result of the load. The next part is the bulge area, and this area, as we can see here, is full of some major anticlinal and synclinal faults, as well as some salt domes. Let's dive in detail into the fold and the thrust belt and foreland basin. Here is a section from the eastern part of the UE, and as we can see here, it has this part which is full of mega thrusts and folds. And also we have here the foreland basin. Imagine that the foreland basin, the basement that we mentioned earlier about, the basement could reach up to 18-kilometer depth, which gives the indication about the huge tectonics that happened across this area. Let's look in detail. Don't worry about these details, I'm not talking about this, but let's have a simple look at this. These are some drilled wells in the eastern parts of the UE, and we will look into these two wells here. You see these two wells are separated by only 14 kilometers. And when we look at this stratigraphic unit or geologic unit, you see that unit, it's the same unit. It has at the same level. This unit was at the same level, imagine, and then it has been pushed upward to reach this difference. You see the difference is more than 3 kilometers. So imagine the force that created this event or this situation. This event actually, which is its age started from the late Oligocene to early Miocene time, which is around, you can say, around 24, 25 million years ago, and resulted in the collision between the Eurasian plate and the Arabian plate, which we know as the Zagros collision. So how we can see these features in the subsurface? We actually can identify these faults and structures in the subsurface. We use some geophysical data. Here is one example of gravity method. We measure simply the gravitational field of the Earth, and we can use the gravitational data to do some inversions and calculations to get like this some 3D models of the Earth's subsurface in the UE. This is the eastern part of the UE, covering this part. This is a line. We have a line here, and this is the border of UE. So this area covers the eastern part of the UE, covering the fold and thrust belt and a part of the foreland basin. Also, we have some data for seismic reflection. Seismic data is basically we measure, we generate like artificial earthquake. You can just simply hit the ground and see how the Earth would respond to this. From this data, we identify the different structure within the fold and thrust belt. As you can see, the different faults and folds. Let's move to the western province, or the western area. The western area, as I mentioned earlier, is full of anticlines, and most of these anticlines are currently oil hydrocarbon fields. as the oil and hydrocarbons in general prefer to migrate to the top part of these structures because this part is much closer to the surface, which means less pressure. So they travel from the deeper parts with the high pressure into the low pressure areas. Also, this western province has salt domes. Here is one example of Dalma Island and Jebel Danna salt dome. An interesting fact about this is the salt dome, while coming up, while migrating from the deep subsurface, it brought very, very old rocks, maybe more than 500 million years ago. So it brought some classes, as you can see here, from the subsurface. As you can see also from this part, we have the very deep basement here, and the salt, while migrating upward, it brought some classes, some old classes. I don't talk in detail about this, because Cosmos already mentioned about this quakes. So most of the area is very stable because this area is very stable. The collision already happened along this part, and we have the major activities in Iran. But also we have very minor magnitude earthquakes in the northern Emirates. And possibly now you know why we have the earthquakes in the northern Emirates, because we have here the fault thrust belt. Most of the work that I have shown is basically from my two papers, from my PhD papers, published in Tectonics and Tectonophysics. Here I go to the next part of second part of my talk, which is the discovery bookmarks and seafloor gas seeps. Here I'll go back to, if you remember, the hinterland basin. This area is a part of the hinterland basin. This is a study area that I'll talk about that we studied recently. So I had actually the pleasure and the honor to go on board the Ocean Explorer vessel in 2023. This vessel is a very huge research vessel. It has remotely operated vehicle. It has even two submarines, and also have some wet and dry labs. We acquired several data on board of this vessel. The first thing is the multi-beam bathymetry. So multi-beam bathymetry is very simply, look at very simple physics. It sends down from the vessel some high frequency sound wave to the seafloor, and these waves bounce back to the vessel, and we just measure the time, the travel time, so we can identify the depth of the seafloor. We have also acquired some water samples across the water column, and also we measured the physical parameters of the water column from the seafloor to the sea surface. And also we went down with submarines to acquire high resolution videos and got some samples from the seafloor. We also acquired some sediment core from the seafloor. We send some tubes like this and push them into the seafloor to get like a core of the seafloor, and getting this core would give indications about many things like the climate change in the last few hundreds of years. So I'll explain this term now because I mention it frequently, seafloor bookmarks. What's a seafloor bookmark? Imagine that we have a source of gas in the subsurface, and the gas migrates upward, reaching to a certain level before the surface, and it got trapped by some layers. It couldn't escape to the seafloor, but it got trapped in the subsurface. After trapping and escaping of more pressure, since we have like any fracture or conduit, the gas would prefer also to go up, even if this area is closed, is trapped, but still the gas have area with low pressure, so it prefer to goes up. While going up, more gas is coming up, So it will make like overpressure area like this, as you can see here. At a certain stage, the overpressure will be released, and we get like this depressed area, which is called the bookmark. But of course, this overpressure explosion it's not like a balloon, it's not and it goes. No, that's very it's not very, it's a slow process. So let's look at the bathymetry data. Let's dive into the seafloor of the offshore Fujairah. Let's dive together and see. We have here, this is the shelf area. This is the shelf area. And we have here the shelf break. Then we have this slope, continental slope, and maybe part of the deep seafloor. Let's go in detail, closer. We can see several features. These features look like maybe channels. In some parts look like holes, maybe, as you can see. Let's move on. Big channels, as you can see. I'll explain what are these features. We have some holes also in this part. We have very minor holes in this part as well. So what we identified in this area is around 1,000 circular bookmarks, more than 1,000, and also crescent-shaped bookmarks. As well, 70 areas with complex bookmarks. You see, these are the circular bookmarks in the seafloor. We have more than 70 areas with complex bookmark strings or eroded bookmarks. The first thing here is the circular bookmark. As we can see, here is the distribution of the circular bookmarks that we identified in red color in this part. And you can see the slope gradient. This is the slope of a gradient map. You can see the different slope, and the bookmarks, the circular bookmarks have like a flat bottom. Next part here is the crescent-shaped and bookmark strings. Let's look at this. It's the same bookmark, but this one has a crescent-shaped. And if we looked at these longer that we have seen, seems like a channels, we can see that this is the same like this one and also this one, but these features got elongated by some forces. The most interesting thing is that here we can see this is different kind of data that we collected. This very bright surface is a seafloor, and when we look at this, we can see some like high backscatter columns coming out from the seafloor, and these are basically the active gas bubbles or the active gas seeps that are coming out of the seafloor. We identified around 35 locations with these gas seeps. So one question, do we have a gas in the subsurface? Yes, we have some subsurface data, some seismic data, and in that data, we were able to identify local accumulations of gas in the subsurface. As you can see in this part, we called it like a bright spot. So we have several bright spots. We have also some conduits that could allow the gases to escape from the deeper parts to the shallower parts. We have also this area, it has like turbidity in the resolution. It's actually because of the migration of the gas along small conduits. So how did those bookmarks get elongated? The elongated bookmarks that I mentioned in this part, how these got elongated? These are the physical parameters of the water columns that we measured at different locations. And we simply graded the physical parameters together. We have like one profile here, one profile there, and we graded the data in between. And here you can see there is a kind of body in the deep water. Just to know, this is the seafloor here. This is seafloor. And we have this deep body here is coming out of the Arabian Gulf. This section is crossing, the main section is crossing like this, from the north to the south. So it's coming from the Arabian Gulf down to the Gulf of Oman. These parameters, or this body, has high salinity, high temperature, and also high beam attenuation, which gives the indication that it's the same like the Arabian waters, the Arabian Gulf waters. So this is a deep flow of the Arabian Gulf. This deep flow of Arabian Gulf, at some stage here, with the bookmark is created like irregularities in the seafloor. So the current, while traveling, when it finds, when the current finds some irregularities, it started to make some eddies, and the eddies makes these bookmarks to get elongated. So what's the trigger of gas seepage? Why we have this gas seepage exactly in this area? Let's look at the regional map. Again, this is the UAE border. We have a line here and Abu Dhabi here. Let's look at the regional. We have a major normal fault along the coast of Oman, and this fault makes the seafloor like to be displaced vertically up to more than 200 meters in the southern part, and the displacement towards the offset decreases to the north. So this fault continues up to the UAE waters, making like a damage zone. It's not exactly a major fault, but it's a damage zone with slight normal, very normal faults with small displacements, and also some fractures that allowed the gas to go up along these features. You can see the trend of these features here is basically going like with this, the same major trend of the normal fault of or gravitational fault. So let's sum up the process of the formation and evolution of the features that we have. The first stage is the formation of the bookmark. We discussed it with the gas seepage. And the next stage is the current erosion. This is the Arabian Gulf outflow. The bottom with the regional currents and eddy currents makes the circular bookmarks to be like a crescent-shaped bookmark. And later on, it could be with more erosion, with more current erosion, it could be elongated. And if we have another circular, another bookmark nearby, they could be connected together to make like a channel. So in general, what are the implications of this? We identified the gas seeps, and what's next? What is the issue is that we have thousands of seafloor gas seeps. Either are inactive or some of them are still active. So we have some gas that have been, went down to the seafloor. We are not sure if the gases are able to go to the seafloor or not. But it's preferable because of the area is actually a part of like a low oxygen area. The waters have low oxygen. So the low oxygen, if these gases are methane, low oxygen environment would give, the chance for the gas to travel to the atmosphere. And this could somehow gives a slight contribution to the climate change, let's say it. And this work actually just has been published a few weeks ago in Journal of Communications, Nature Journal, Communications, Health and Environment. And I'd like to thank my colleagues from Khalifa University and from Environment Agency Abu Dhabi. So do we have that chance for way forward? I can say yes. EED has a research vessel. This is a vessel, J1. Some of you may know about this. And actually, I had just the chance to go maybe in up to 5 or 6 expeditions with G1. So we have the capability for way forward. Finally, I'd like to acknowledge, of course, Khalifa University to support and the Environment Agency Abu Dhabi for funding the Ocean Explorer vessel to acquire the data that we got, and Ocean Explorer vessel crew for the efforts in acquiring the data. And great thanks to my advisors, Dr. Muhammad Ali, the chair of the Department of Earth Science, and Dr. Aisha Swedi at the Department of Earth Science. That's all for my today's talk, and thank you so much.
Thank you very much, Dr. Ahmed, for this really fabulous talk, and congratulations to your research. And I want also to thank again Dr. Cosmos. I think both talks are fitting very well together, and we all learned a lot. And you know, we can also see what modern technology makes it possible to all of us. And I would ask you both to join us here and for a big question and answer.
Fantastic. Thank you so much, everybody, for just the knowledge. And now I know where, as I get older, I think I can feel those tectonic plates moving. Right. So now I've got an excuse when my kids laugh at me. I'll go, ah, no, tectonics. So we're going to open the floor to the panel. I'm sure that some of you have a lot of questions, and I already see hands up. So let's open the floor to everybody. I'll come on over here.
Great. I have a couple of questions actually. So, first, do tsunamis have something to do with earthquakes?
Yes, of course, they have a connection with earthquakes, especially when happen to the seafloor. You can, of course, it's so old for you. It's 2004. Was the Banda Cechin earthquakes by the submarine fault zone, subduction zone, produced a huge tsunami that arrived to Sri Lanka, Phuket in Thailand, and finally in Somaliland, and killed a lot of people. This is a wave produced by the movement of the earth crust or the lithosphere because of the earthquake. And that's create a wave that can travel around 800 kilometers per hour at the open sea, not too much shade, 2-3 meters, but arriving in the shallow water, rising up because of the friction, arriving 10-20 meters. And when you feel the shake, it's okay. You can move to the higher lands. But when after 1 hour and a half arriving the tsunami in another area that didn't feel anything, it's totally dangerous. I would like to say mortal sometimes.
Do they affect each other?
Look at this, yes. The earthquake is the generator of the tsunamis. What happened in the floor of the sea? We have also landslides that the pockmarks, as Ahmed presented before, yes, could be triggered and submarine landslide that produce tsunami as well. And we have also finally the volcanic eruptions. Volcanic eruptions, we will have a lot of pyroclastic material that in lava coming to the sea as in Hawaii, and we have a big slope, submarine slope, and we have instability of the slope and start to slide to the higher depth. Yes, we have another kind of tsunami. No worries about it, especially in the Arabian Gulf, the probability is too small, especially of the western areas and Abu Dhabi. It's really a small probability to have one.
My next question is, did Dubai ever have an earthquake where Burj Khalifa was affected by it, since it's the biggest building in the world?
Look at this. Regarding the construction, it's geotechnical approach. And believe me, most of the high buildings in UAE have a good construction by pillars arriving 30 or 60 meters or more, there are their friction pillars. And after they put a raft and they start to build on. All this construction are made by the high standard specification. And I think I feel more confidence in high buildings than the villas.
Yeah. I can add to Dr. Cosmas that we have here in Abu Dhabi the NCM, the National Meteorological Center. So NCM actually have so many stations for measuring earthquakes across all the UAE, the whole UAE, and they have some stations fixed in some buildings to monitor any movement within the UAE. So don't be worried.
Also, if you like to add and do advertising for LYU Abu Dhabi, they have a huge centrifuge. The centrifuge is a machine that simulates earthquakes based on your construction and provide acceleration of the soil and so on. It's the one on the region. That means there are really good tactics and methods about the safety of the building and the construction.
We have room for more questions. Who is the next one?
I think we have a microphone over there. Yeah. I think we have two people with the mic.
Yeah. So my question is not related to the UAE's perspective in general, but like it's related to more Asia, like the Ring of Fire, and the tectonic plates and the volcanoes there. How do you effectively minimize damage caused to coastal cities there, especially due to how highly densely populated they are?
Very nice question. I kindly ask for Anas to bring me.
Anas, please.
Anas, please. Yes, it's very difficult to answer on that. Look at this. The Earth can exist without us. Probably exist already 4.6 billion years ago. That's mean the Ring of Fire is more complicated, if you like to say, volcanic zone or system that is related with hotspot, as we call it. Thank you, Anas. You can give to him. Here is the center of the Earth, core, the mantle. Sometimes we have some magmatic chamber or plumes that provide lava flow, and that is one case of Hawaii, more complex. And to the other hand, we have in subduction zone, you can see here the subduction zone, that we have a mountain zone and volcanoes to the other side, and that is in Japan the case. And if you ask me how, thank you, Anas. If you ask me how we can really mitigate the damages, USGS led the Ocean Pacific Monitoring Center about volcanoes, and when we have a big earthquake based on a network of seismographs that are already into the seafloor, of course some buoys about the change of the sea level, and all are connected by real-time system, and alert and really serve the alert with other countries if happen one earthquake and the probability of tsunami. Sometimes they fault about the tsunami, but in other cases, yes, the alert is really effective. A tsunami to travel in Pacific Ocean, depending on where you are, could be from a couple of minutes, 30 minutes, till a couple of hours. But if you ask me about the impacts to the global system, if you have a huge eruption as Tunga in South Pacific, you cannot minimize. Okay, you can save your life, but you cannot stop the climatic variability impacts by a volcano. You cannot trap the gas, it's crazy. That means we must be adapted and try to live with all this volcanic tectonic activity, live in our planet.
So I'm gonna cheat a bit here and ask a second question.
Please.
So you mentioned about how to survive, so that how people can survive. But like, what about like from an actual city perspective? Because 80% of the world's population is gonna live in cities.
It's a very good question.
Yeah. So like during rush hour, it's like impossible to get into high rises. And
look at this. If you feel the same, that's mean, and you are near the sea. The wise idea is to move into the higher altitude. Here is a little bit difficult. Huh? The higher due near the coastline is not more than a couple of 2-3 meters, or go to inland. You cannot say that a city if you build walls. But the key point is to do wise urban planning if you are really affected by the earthquakes. And you have also, as I think Mark, Dr. Mitz would like to ask about the records that we have from the old culture and civilization, how they survived on that. I would like to give you an example. 3,650 years ago, when we had the big eruption in Santorini and affect all the South Mediterranean and the Levantine Sea, and cover the ancient city of Akrotiri by more than 10 meters of pyroclastic material, no one guys died. They was really informed based on their tradition, and they leave this island by boat and save their lives. The archaeologists didn't find even a precious object of gold, nothing. That's mean the key point is to the preparedness stage. Be prepared based on the hazards that we are exposed.
Thank you.
Thank you very
Getting
much
some
for your
great questions, yeah, aren't we? Let's move to the side of the room. I think we had some people here that had some questions. Questions from the side? Somebody back there.
I've seen about the salt domes, so I'm just interested to know how it's formed and what causes it to rise up and actually cause the movement.
Okay. So as we know that the salt has less density than the other rocks. If we just imagine that we have a sample of a part of granite, like a granite, and the salt. So the granite has a higher density. So now let's imagine that we have a low density layer that's buried by higher density layers. So it's buried down and it feels like compressed somehow. This layer won't find any differential pressure around or any weakness across the Earth's crust. It would prefer to escape upward, to migrate upward. And while migrating, it just opens this fracture more and more and more to form this shape of salt dome. Of course, it will at some times, as we see in the UAE, some salt domes could go up even to the surface, but other domes could travel within the sedimentary sequence, but do not travel to the to the Earth's surface. Yeah, so it's basically because of differential pressures with salt that has low densities compared to the overlying rocks.
Thank you.
Thank you.
Yeah. Somebody in the middle over there.
Hello, and thank you very much for your talks. You mentioned the gas. Do we know what kind of gas? Is this methane or CO2? And another question, for me this sounds like a cheese, with all these holes in it. Is this structure now weak and could impact the surrounding and the faults or whatever? Just a little bit insights on this. Thank you.
Thank you. So firstly, about the type of gas, we don't know till now about the type of gas because we just detected the gas actually from some of the measurements after our expedition. So if we knew about the gas, we had earlier the ROVs and we had the submarines. We could go down and check and maybe get some samples. But we actually discovered after our expedition. So we don't know which which type of gas is escaping. But this is something of our plan, our future work, that we need to sample the gas. That's one thing. The second thing, it was about.
No, I mean, it feels like a cheese, you know, with
Yeah.
all the holes now. Is this
Oh, yeah.
structure now, or should we worry? Or
No, it's not big way. The escape of gas and the formation of these features, the diameter of a single feature is 30, 40 meters, and the water depth at these areas is around 200 meters water depth, maybe even more, up to 300 or 400 meters. So that's very far from us. That's one thing. Maybe one thing I didn't mention in my presentation is the same area has some active seafloor faults, but that's an ongoing work, and that's why I didn't talk about, and it's a part of one of my colleagues' PhD work. Thank you.
If you give me the permission to add something, when we have the hypersaline water coming from the Arabian Sea, especially on the continental shelf, sometimes trap the organic material that could be not only plankton or something like that, and that time by time covered by sediments and provide an anoxic condition. It's like I don't like to say landfill of organic material, but that produce probably, you prove to us, that will be methane and some oxide of carbon dependent, something like that.
Yeah, we have some insights about the origin. Could be thermogenic or could be biogenic. Could be thermogenic because recently I published a paper about the petroleum activity, the petroleum evolution in the subsurface of that area. And actually there are some source rocks that could generate some hydrocarbons. So we expect that we have some thermogenic gases. And also looking at the burial history of that area, the burial history in the last few million years is the substance or the burial is very rapid. So very rapid means the burial of the organic matter, very rapid burial of organic matter. The burial of organic matter would preserve it from the oxygen to be consumed by the oxygen. But you know, there is a different process. It's the methanogenesis. So it could somehow, the buried organic matter could be somehow, you can say, transform it into methane, so the methane can go up, and this could be biogenic gas. But as I mentioned, to know the exact type of gas, we need to sample it.
Yes. We have somebody up front here.
I wanted to know where is the largest earthquake in the world?
Nice question for Trevor. Okay, the last earthquake, if I remember well, was in Chile, 9 Richter scale, and if I remember well, one in Alaska. That was at the beginning of the 19th century, 19 something, if I remember well. But you know, we do not have instrumental records. That means we cannot have records approximately, but after the 1920, 1930, we have records about the seismographs that we know exactly the magnitude and so on.
Okay, I have one more question.
Please.
Where was the largest tsunami in the world?
There are a lot of large, existed a lot of large tsunami. One of the largest one was, of course, in Pacific Ocean, because we have the volcanic arc, but archaeologically and historically documented was in Eastern Mediterranean by Santorini volcano. The explosion that really affect all the Eastern Mediterranean. And Eastern Mediterranean means Egypt, Alexandria, means Palestine, means Lebanon, Syria, and so on.
So most of the largest tsunamis are by Santorini? Like around
Yes, because of the eruption of the volcano, after the seawater coming inside, there's a secondary eruption. Huge amount of volcanic ash and lava go to the sea and destroy, create a huge tsunami. There are estimation about 30, 40 meters, only modeling. Nobody was there. We found and we find till now some records on the coastline. What I can say to you with precision that I studied last year was that at least 5 to 10 meter tsunami was from the same area was really documented by the volcanic deposit on the coastline of the surrounding islands. Because we found the volcanic ash, we take the sample, we analyze in German laboratories, and we recognize the same imprint of the eruption of the 1650 before Common Era. That's when 400 years ago. We work like that.
We've had a hand up for a while over there. Guy in green over there.
I wanted to ask, like, what if the volcano in the ocean, the island, can you not just hide, like, behind the mountain? Because the picture, like, showed a mountain, and can you not just hide behind the mountain and then it wouldn't affect you?
I think the question is if you can hide behind a mountain to get away from the volcanic activity if there's a huge mountain behind. Is that correct?
Yeah.
Of course, the volcanic activity can provide high mountains. That's Mauna Loa in Hawaii, 4,000 plus meters. But during time, we do not have only the internal processes that construct mountains or build mountains. We have also what? The rain, the wind, the temperature that we have, weathering of this degradation of the mountain. And that if the volcano is active, it's growing up. If it's not too active, starting the atmospheric processes, that means the weathering, like a caterpillar, eat the mountain and starting to be lower, degrading, and so on.
But can you not just, like, build a high enough wall to, like, stop the ash?
Stop the lava. That's dependent on the processes. That's mean if we have a hot spot and the ocean floor is moving apart, once upon a time, the big magmatic chamber, like a pot of magma, go farther for this volcano. That means no feeding with lava. That means starting to be inactive and starting to be degraded.
And the third question, what if you just build, like, a super high wall and then you can stop the tsunami?
Super high wall to stop the tsunami. I think we're
Nice subject for a movie.
You know, certain forces of the earth we cannot stop. We are just humans and we have to accept it. If there's a huge eruption, we have to accept that we have to go out of its way, and just try to be as safe as we can. But nature is not in all points controllable.
And of course, we are something like that about our power, energy, driving forces. Earth system is huge, and that we do. The scientists is try to understand, try to monitoring, and alert. In any case, bigger volcano, super volcano as we have is Santa Helena in northwest Yellowstone Park. Earth scientists know that every 650,000 years approximately give a huge eruption that can really change our civilization. But nobody knows when and how.
I think the great learning opportunity here is it's very hard and impossible and should be to control nature, but and to stop nature. But we have it in our power to stop the effects that we have on nature. So it's going to be ultimately what nature has in store for us. I think we have place for one more question over here. Let's see.
I wanted to ask, what is worse, a normal volcano or underwater volcanoes?
Nice question. If you're adding not the vulnerability, but the hazard that they provide, if we talk about the same magnitude, of course, a submarine volcano can provide a big, huge eruption, provide volcanic gases to the atmosphere, and tsunami as well. If you have a land volcano into that, can really provide huge amount of volcanic gases of the atmosphere, trends, lava flow, and everything about that. Dependent the mechanism, but dependent the processes. And of course, how many people and population lives on the surrounding areas, especially in coastal lines.
Thank you.
It's amazing all the wonderful questions we're getting from the young people in the audience. I think they've asked all the questions for the adults here, but I'm going to see if there's one more question from one of our adults in the audience. So, adults in the audience. There we go. There we go.
Yeah. So it's me again. I noticed that you avoided the situation in Greece in a moment. So what is your take on this now that we can finalize?
Yes, I put out of my presentation because it's a very specific subject. If you would like to visit Santorini, delay a little bit. That's been cancelled for the next months. Nobody knows exactly of my colleagues. We work there thanks to one of my PhD students in Greece who worked last year and try to determine the risk zones. In brief, is what is swarm earthquakes that triggered by the magma below and stress the small length fault about 15 to 20 kilometers on the upper lithosphere, 5 kilometers, 7 kilometers, 10 kilometers, that activate them. The key point is that if stay till now, could be continue a couple of months. But nobody knows, because we do not have early warning system, either real-time observations, to know if that will be worth it or not. And we are expecting with Geomar coming beginning of the Mars to putting out, lift up our sensor on the bottom of the Colombo volcano, which is the northeastern part of Santorini, and try to read the last 6 months data. The real answer is nobody knows when, where, and how, to be honest.
Well, from the SeaWorld Research and Rescue Center, we'd like to thank you so much to our esteemed guests for just the wonderful talks this evening. I'm sure for those of you that have a few more questions, there will be some availability afterwards. I want to thank you all for joining us and participating in our monthly talks. And we'd love to see you all again in the next talks. Look out for what's coming up. We've got wonderful things coming up. I have a hint of dinosaurs around the corner. Anyway, thank you so much for coming, everybody, and we look forward to seeing you again. Thank you.